Okay, so today we're going to keep kind of continuing this theme of sort of this ambiguity of whether or not some problems are solvable or not. But otherwise, we'll look at compared to last time, we'll look at a problem that takes place in graphs. But yeah, just to review, this theme sort of started just looking at simple Boolean logic problems. If I give you a Boolean formula, can you find something that makes it output true? Right, which in full generality sounds pretty hard. But nonetheless, that's sort of like this big central question, right? So, is there a polynomial time algorithm for this problem or not? One thing nice about this problem is that Boolean logic is sort of exactly what computers should be good at. But somehow it doesn't seem like there's enough structure to get something out of it, at least so far in our discussions. What is maybe more surprising is that when we start looking at special cases like 3-SAT, so I put it in conjunctive normal form, so it's just an and of ors, and there's only 3 variables per clause, even that we don't have an algorithm for, but we have some explanation. You can actually take any Boolean formula and rewrite it as a 3-SAT problem. Sort of extending this discussion was like 2-SAT versus max 2-SAT. So 2-SAT you can actually solve. You can draw up some kind of graph. It almost becomes a reachability question. But max 2-SAT you cannot solve. Somehow that max gives you like half a degree of freedom. And that's somehow enough that you can pack 3-SAT into max 2-SAT. Okay? But all those things that came before the midterm, at least we're always working in terms of Boolean algebra. So there's a little bit more connection between the problems. Last time we did something that's maybe a departure from that. We looked at subset sum, also a very simple looking problem. I give you n numbers and a target. Can you find a subset that adds up to the target? That you would also think that computers would be good at. And the numbers are actually really small, then you can just do a dynamic program. But it's not really polynomial time once the numbers get big, because running time will depend on the magnitude of those numbers. And what we showed instead, which I think is very surprising if you haven't seen it before, is that subset sum can be used to solve 3-SAT, and thus it can be used to solve kind of Boolean formulas in general. And the starting point of the trick was like, oh, actually, an n-digit or n-bit Boolean number, actually, those individual bits, we can kind of pack in a lot of logic where each digit is sort of kind of enforcing some logical rule. And then gradually we can stuff an entire 3-SAT problem in there. There's some cleverness like the padding and stuff like this. But the point is that even these sort of things we take for granted like integers can sort of be arbitrarily complex as well. And that suddenly makes this question of like, oh, I give you some simple looking problem, can you solve it? That makes everything much more rich. So, all right. So today I'm going to give you another problem that looks just as simple, which may or may not have a good algorithm for it. But we've done shortest path. I think this is even the same graph from some shortest path problem before. But now we're going to do longest path. Okay, so path means I also can't revisit vertices. But I give you like a directed graph. Maybe for simplicity, there's no edge weights. You could have edge weights. And I just say, what's the length of the longest path in the graph? A special case is if there's a path that visits all the vertices, and that's called a Hamiltonian path. Okay, so the question is there a Hamiltonian path in the graph? Okay. So, right. So, okay, here's maybe an example of a graph, and just to make sure we're on the same page, I'll let you stare at it and try to come up with the longest path you can find in this graph. What's the longest people have come up with so far? I actually don't know the answer as usual. Oh, no, there's only 14 nodes in this graph. It's not the biggest graph in the world. I think there's 14. Anyway. All right, what you get? Oh yeah, I don't know if there's a Hamiltonian path, but what's the longer? Yeah, there's probably not a Hamiltonian path, but what's the longest anyone got? There's no wrong answers, but yeah. Okay, 6. Where should I start? Here? Okay. Left, bottom, right, right, down or something. So that's 1, 2, 3, 4, 5, 6 edges, 7 nodes. Anyone beat 6? Yeah.
I got 9 by just backtracing that 3.
Backtracing. Okay.
So I started like 3 nodes sooner.
Okay, so let's go backwards from our start. So like this way, you're saying?
Yeah, and then down to the right.
Like this. So now we're up to 1, 2, 3, 4, 9. Did anyone beat 9? Yeah.
Instead, start at the purple ones, or like consider the yellow path and start at the purple, like take a right.
Okay, so I'm gonna go from here. I'm gonna take a right,
Then take a left,
left, down.
oh, so never mind.
No problem. I guess that's tied for the same. Anyone do better? Yeah.
Instead, we're going to visit to a vertex twice.
No, so this is strictly for paths. So you can't visit a vertex twice. So in this class, we'll always be very careful. Path will always means you don't visit a vertex again, and walk means you're allowed to visit a vertex. In the literature, sometimes it's looser, but we're here we'll be strict. Does anyone beat 9? I don't actually remember what the right answer is. Okay, let's say it's 9. I don't know. But okay, in any case, it's not that easy of a problem because there's only 14 nodes and it seems quite challenging. Okay, so we're going to look at this problem in 3 types of graphs. One is a directed acyclic graph. Another is a directed graph like you just did. And then the last one will be an undirected graph. Okay, so 3 different problems. They may have different behavior, and we'll see. And for each of them, we're either going to come up with an algorithm or some justification, maybe try to show that giving an algorithm would give you an algorithm for a SAT. Okay. All right, so it's also going to be a study of graph structures and how that can affect some complexity. Okay, so we'll take a vote as usual because that makes me feel like I'm teaching. You're allowed to not vote, of course. Who's not going to vote? 1, okay. It's a lot of pressure on the rest of you. Okay, so for a DAG, who thinks we're going to get an algorithm? Oh, a lot of people. Okay. All right, and then how many of you think we'll be able to show it's hard? Okay. All right. Did I even do the math correct? Okay, I did. Okay. All right. So now slightly more general, directed graphs. Who thinks we're going to get an algorithm? Okay, fewer. Okay, and then who thinks it'll be hard? Okay. All right. Last row is undirected graphs. Okay, so who thinks we can get an algorithm for undirected graphs? 1, 2, 3. Okay, so I'd say that's like a little more ish. I don't know. And who thinks it'll turn out to be hard? Okay. All right. So this actually is at least a sensible set of votes. Like, for example, a directed graph is more general than a DAG, right? So if we get an algorithm for a directed graph, you'll get an algorithm for a DAG. So it should be like this. Like, there should be more people thinking there's an algorithm for a DAG than for a directed graph. It shouldn't be opposite. And undirected also, if you can solve directed, then you can always solve undirected because you can kind of replace undirected edge and undirected edge with two edges in both directions. So an algorithm for directed will always give you an algorithm for directed. So this percent should be a little bit higher than here in any case, regardless of the outcome. Yeah.
Do we have to consider like the conversion of the directed graph into like the undirected graph in the runtime?
Uh, yes, but did you mean converting directed to undirected or undirected directed?
Splitting each like directed edge into multiple undirected nodes. Oh wait,
Or you mean converting undirected to directed? Yeah, but the running time won't be so bad because you just look at each edge once and you create twice as many edges, same number of nodes. So, that probably won't be the bottleneck of your algorithm. Okay, all right, but okay, that's the lay of the land. All right, so I think we're going to start with DAGs. Okay, and of course, DAG by definition means there are no cycles. So our problem is basically the same as asking for the longest walk in the graph, right? Every walk is a path, every path is a walk. But at some level, you don't have to really worry about this constraint of revisiting a vertex because you can't do that in a DAG anyway. Okay. So for this, we're actually going to try to develop, oh yeah? For this, we're going to try to develop an algorithm. But does anyone want to propose an algorithm or an approach? Yeah.
Create some source that connects to the sources.
Okay, so the suggestion was maybe I could make a super source attached to all the sources and run DFS. And DFS will figure out everyone S star can reach, which I guess in this graph will just be everyone, right? If you ran DFS in this graph, it's going to go find all these connections or something, right? But how does that relate to a path? So you'll say, okay, the super source can reach everyone, which is actually almost immediate. As soon as you attach a super source to all the sources, you are, I think, by definition of source, going to be able to reach everyone. Oh, unless there's, yeah, no, yeah, okay. So, okay, you can do that, but it's not going to tell you much about the longest path as far as I can tell. Yeah.
Can we find the longest like path from the sources to the sinks?
The longest path from the sources to the sinks. Yeah, so at some level, you can try guessing like the first and last vertex of the longest path, and there's only n squared guesses. So if you can just solve this particular starting and endpoint problem, then you'll still get a polynomial time algorithm overall. But then you still have this question of, if I gave you the endpoints, the longest path, can you find the longest path? Yeah.
You just do Bellman Ford, like a Bellman Ford thing, where you fill the verses to 0, then follow the edges to add 1, then follow the edges to add 1.
Okay, can you do a Bellman-Ford thing where you set all the vertices to 0 and then you add, well, yeah, maybe we can expand a little more.
Yeah, like you have all the vertices at 0, and then you're going to add 1 to all the ones that are connected to, or I guess they should still be 0. But you can add everything that's connected to one of the sources, add 1 to all those edges. When everything got updated, you go to all the things that the edges go to and add 1 to that one, and whatever it was initially. Like, and then you just take the back, so it's already like a 3. You don't update it if you have a 1 going to it.
Okay, so maybe to try to clarify this, what would like the subproblems be? Like the Bellman-Ford originally was like, what's the shortest distance from S to V using at most 5 edges and 6 edges? So then it was very clear, right, what the algorithm is. What would your problem look like? So I get that you're kind of doing something recursive-ish and you're trying to propagate some values, but to make it clear, you want to take a stab at it?
Yeah, it's like, what's the, if we only go X distance from the source, what's the longest path that we can reach this vertex?
Okay, so okay, so you have some like all right, BW for Bellman-Ford, and then you have some vertex and some number of steps. And so and then so what would the sentence be for this vertex and this value of k?
Returns the maximum number of steps to reach the vertex with that many steps.
All right, so max length of any walk to V with at most k edges or something. So this value is always at most k. Okay, so then you can imagine like, oh, once I figure out k minus 1 and who I can get to in k minus 1, then I can maybe try to figure out k or something like this. Did you have another idea? Yeah.
But set like every equate to -1. So that's the shortest path would be like the most negative, like it's like the most edges.
Okay, so maybe another trick we can do is we can set all the edges to -1. And there's no cycles here, so there's no negative cycles as well. This will work. And it might end up kind of replicating the exact same logic as this thing from before. And then I'll maybe also add a super source or something, and I'll put another -1 here, which means my answer might be off by 1 at the end, but then you can just add 1. So if I put -1 everywhere and I just ran Bellman-Ford, we don't have to make any new algorithms, which is, of course, what we always encourage. Then this will just look for trying to get as many negatives as possible in a path, which is the longest path, right? Okay, so that will work. And how long will that take? What's the running time of Bellman-Ford? Sorry? Well, I guess it'll be on the cheat sheet in the exam, so you don't really have to know. But it's MN, right? Because for number of steps 1 through n, you always do one pass through the graph. You look at all the edges once. Okay, so that's MN. That algorithm will work, and there's almost nothing to prove because Bellman-Ford's guarantees are so strong. Okay, now you can actually do a little faster. Okay, does anyone want to try to do it faster? Yeah.
And I get some at the beginning at the source, or like a super source, then you can check its neighbors. You take the max out, 1 plus, and then the graph and out that neighbor.
Okay, so if we want to do something like DP, of course we just did DP, but we're going to do an even more direct one. Okay, we'll start with which is essentially a recursive algorithm, but we save our answers. We'll start with some kind of recursive spec to model our subproblems. Okay, so I understand your algorithm, but like, what was the sort of a subproblem that you had in mind?
It would be the longest path, starting at this source.
Yeah, so maybe LP for longest path or something. I think the next slide actually says longest walk, but maybe like I'll just return the length. You know, I'm at some vertex in the middle. The length of the longest walk starting at V. This is almost like simpler even, or more direct than Bellman-Ford. Okay, so just for every possible starting vertex, what's the length of the longest walk starting at that vertex? Okay. All right, so, all right, now if I want to implement this, I know you said it out loud, but I'll coax you guys again. So I just want to find for a given vertex V, what's the length of the longest walk starting at that vertex V. You know, ultimately going to apply it to a source, but maybe you're at some point in time in the middle of the graph or something, right? So you're at some generic vertex. How can I kind of recursively figure out the length of the longest walk from V? Yeah.
It's one plus length of all its children.
Yeah, all its children are like outgoing edges, something like this. So I would check all the outgoing edges and recursively check, oh, what's your longest walk? What's your longest walk? Something like this. So maybe 1 plus the maximum over all maybe edges from V to W, longest walk from W. Is that what you had in mind too? Oh, okay. Okay, maybe only one very minor bug. It's hardly a bug, yeah.
If it's a sync, you're returning zero.
Yeah, so if it's a sync, maybe you return 0. So maybe I'll write 0 if V is a sync, and then otherwise normally you put the otherwise second, but oh well. So if V doesn't have any outgoing edges, then like this max thing is like a little bit awkward. So if V is a sync, I'll return 0. Otherwise, I'll look at all my outgoing neighbors. I start here, I take some step, and okay. All right, so simple enough. Okay, so let's say, naively, if we didn't do any dynamic programming or caching, then this will take a very long time because you're exploring all these paths in the graph. It'll take exponential time in the worst case. But we can save our answers. And maybe this is something important to point out. So when we've done dynamic programming before, often our subproblems were like, they basically all took place in arrays so far, right? So there's always this kind of rigid, sort of rectangular looking structure or something, if there's 2 indices, or a cube if there's 3 or whatever. But here we don't have, it's not really like an array or something, right? But you can at least look at it and be like, well, there's no cycles. Like there's no, we're not going to get an infinite loop in this algorithm because you can't cycle in a DAG. So at least that's okay. But now the question, I'm claiming that maybe you can do dynamic programming and caching and stuff like this, but there's sort of like a buzzword that lets us do it. Or some level, okay. Or maybe, okay, I'm not doing a very good job. But at some level, okay, so DAGs have a topological ordering, right? And that topological ordering gives you your sense of the subproblems, right? If I'm looking at the first, some source, it just depends on everything else that's down the line in the graph, and this depends everything else that's down the line in the graph. So as soon as you have a DAG, you can order all the problems where there's no cyclic dependencies, okay? And at some level, this is almost the most general form in which you can have basically any recursive algorithm, but especially dynamic programming, right? Like if you have any kind of cycle, like take any other dynamic program problem we've done and think of every subproblem as a node and think of drawing an edge whenever one subproblem uses another subproblem, right? And that graph can't have any cycles. That auxiliary graph can't have any cycles, or else you have an infinite loop in your algorithm. So there's always been an implicit DAG under the hood, which sort of justifies everything. You'd always be able to order the problems, like a topological order, where there's sort of clear base cases that don't depend on anything. Those are the sinks of this sort of auxiliary graph working back up, right? So some level, whenever we give you one of these problems, you're sort of asking yourself, is there like an underlying implicit DAG, where there's some kind of compact number of states and no cyclic dependencies, so to speak. Okay. And then this will be, your canonical example because you're directly on a DAG. All right, so that said, so I can apply caching, right? So basically I'll solve a vertex subproblem and I won't solve it twice, right? Once I compute the longest walk from a vertex, I just save it in a table. You can do the topological order and make an array where each vertex occupies its corresponding spot. But in any case, what would be the running time of this algorithm? Yeah. Oh, what? Sorry, those 2 letters sound the exact same. Which one? N as in vertices? Okay, so there's one problem for every vertex, right? And that's the idea. Except how long does it take to solve one of these subproblems? So we do have a loop here over all the edges leaving the vertex. So it's not a constant, it's not necessarily a constant time subproblem, right? So Okay, so as usual, we're basically just adding up over all the subproblems, what's the running time I spend in that subproblem. Okay. And how might I, how much time do I spend on a particular vertex? Yeah.
Exploring all its neighbors, like maybe multiple time being of n possible.
Yeah, so that's what we'll get there. One step at a time, you're doing some work proportional, to the degree of the vertex. I put a 1 there because otherwise a 0 gets a little awkward. But you're looping over all the outgoing edges. And then as pointed out, so if you sum up all the ones, you'll get n. If you sum up all the degrees, you'll get the number of edges. I mean, we've seen this before in like Bellman Ford and stuff. So overall, you're going to get an m plus n running time that's probably m in most cases, but okay. So in fact, you can do this longest path thing in a DAG in linear time. Okay, so if you have a DAG, then each vertex can be a subproblem, and then you're largely exploring the long edges, so you'll often get a very fast algorithm in DAG. Not always, but often, yeah.
So the one we're doing that encompasses the edges is the max version itself, right?
Yeah. So, I mean, I write it this way because it's kind of easier to see the logic, but it does hide, not make explicit the fact that to compute this max, you got to loop over all the edges.
Well, I guess like even if you're looping over the edges, in the end, inside each like iteration, it's all like a different subproblem. Right?
Yeah.
So like, why do we count that work in like my subproblem as opposed to the next one?
Sure. So I do think of like actually computing LW of W as in its own subproblem. But then here from V, I need to retrieve the value of LWW. That's what I'm really paying for, is just going across the edge to look up the value, going across the edge to look up the value. I mean, you're going to look up, 10 values if there's 10 edges, right? That's all we're really saying. Okay. Any questions? Okay. All right. So that's how, so much for doing algorithms. I guess, okay. I've already kind of said this out loud. But yeah, so topological order lets you do induction, lets you do recursion. You don't have to worry about infinite loops because there's no cycles in the graph. And then dynamic programming will get you all these efficient algorithms, often linear time by roughly the same dynamic. Okay, right. So I think a takeaway is many problems become easier in DAGs, and you should watch out for that forever from now on. Okay, good. So, all right, so let's go back to what we had before. If I remember correctly, this is like maybe 18%, 80% or something. All right, so our goal is to now try to get an algorithm or show that directed graphs are going to be hard. Well, most of you thought it was going to be hard. And I don't even know if there's point in like reevaluating the pool, because it seems like you guys have figured out if the first half of the class is an algorithm, then the second half is going to be hard. So you probably aren't very swayed by whatever we already did. Okay, so indeed, right, we're going to try to figure out if a directed graph has a Hamiltonian path, and we will show, as many of you anticipated, that a polynomial time algorithm for SAT will give you a polynomial time algorithm for finding even a Hamiltonian path, which is a special case, will give you a polynomial time algorithm for SAT. Okay, it's a special case because if you can solve the longest path problem, then you can just see if you can visit n vertices by. Okay. All right, so that's what we'll do next. This will be, like last time, a bit trickier. Okay. But at some level, we're going to start with some kind of SAT problem. And somehow we need to convert that formula into a graph. So this will be jarring just like last time. Last time we took a SAT formula, turned into a bunch of numbers, which would seem completely unrelated. And today we're going to try to figure out how to take a bunch of formulas, or a formula with a bunch of variables, and turn it into a graph, which would seem completely unrelated. Okay? And somehow we should put that into some kind of black box that knows how to solve Hamiltonian path, and the answer from that black box should somehow solve the SAT formula. Okay. And then, the real takeaway is sort of like we discovered with numbers is that, oh, maybe graphs can be fairly sophisticated and complex too, right? Because up to now, graphs have always been our friend. The shortest path problems with all these silly word problems and stuff. Whatever story I gave you, you can make some graph and you can solve it or something, right? But here we're going to find maybe there's some limits to this. Okay. Is the setup okay? All right. Okay, so you start with some formula, right? And then when I'm trying to do a reduction like this between, unrelated looking problems, at least one of my sort of heuristics is like, oh, can I at least try to map like decisions to decisions or something, right? And I think this part's actually gonna be trickier than last time. But yeah, in a formula, each of these xi's represents some decision, right? You're gonna set it to be true or false or 0, 1 or whatever. And somehow you want to try to encode that in some graphical language related to Hamiltonian path or something. Now, subset sum, you all keyed in on like, well, I can kind of think of taking a number or not as at least a binary decision. And that was a little bit more straightforward because subset sum also had this taking or not taking kind of feel to it. But Hamiltonian path, I don't know, well, maybe it's obvious to you. This was where I was going to open up for discussion. Any ideas basically for how to get started or even trying to think about how to try to encode decisions in a graph? I'm speaking, of course, very abstractly, but I don't know what else to do, so. Yeah.
You could like have it split and then go down either like one of two long lines of vertices, and like one of them represents xi, one of them represents not xi.
Okay, so I could imagine, sort of giving two different routes, right? So I think a key thing to get us started is the number 2. Like, okay, you have two choices. So you're imagining something like this. And if, one of these can be, if I take this top one, that means I'm setting, the corresponding variable to be true. And if I take the bottom one, I'm going to take the corresponding one to be false or something. You could imagine doing something like this. Okay, now maybe I want to point out, well, okay, so that I think absolutely is a great start, right? Because at least we have somehow found some way to express, a binary choice in a graphical language. Now, when it comes to Hamiltonian path, really the question is whether you can visit all the vertices. So for this particular idea, it feels like if you take, say, x1 equals true path, you'll never be able to take x1 equals false, assuming things are kind of correct if we imagine pushing this all the way through. And so there will be all these kind of unvisited vertices, and you're just always output, there's no Hamiltonian path, because you shouldn't be able to set true to be or false anyway. So I want to come up with, this is absolutely a great inspiration. I think what we eventually do is we'll have some similarity to this. But in this particular example, our real challenge is visiting every vertex exactly once. And here, it feels like you take one path and you're just not going to be able to visit the vertices in the other path. So, yeah.
You could encode a path as, say, some vertex v, whether it's taken at like the first step or the second step or the third step. So like, and you would create this for every single vertex, perhaps.
Okay, so maybe if you're going to have to visit every vertex anyway, something to do with the order in which you visit things maybe would be helpful. So, yeah, I think that's actually pretty close. So what we're going to do is we're going to just, for each variable, make a very long path with edges in both directions. So you can go from right to left or from left to right, okay? And I'll say like, oh, if you go from left to right, I'm going to interpret that as setting 0. And if I want to go right to left, I'll interpret that as 1. I mean, at this point, we haven't seen the whole construction, so it might be a little bit confusing. But just at this stage, once I created this long path, a Hamiltonian path has to visit all the vertices one way or another. And if really the path is all that's there, you can only go in one direction or the other, because you can't like U-turn, you'll revisit a vertex again, right? So setting up a long path with both directions at least sets up a binary decision. You're going to have to go from left to right or right to left. And then one of them will interpret as xi is true, the other one will interpret as xi is false. Okay, so that's the kind of the starting gadget. Okay. And and what we're going to do is we're going to kind of hook them all up in like a ladder. Okay, so this is just kind of gradually setting things up. So for every variable, I'll make one of these paths. And now in light blue, I've sort of like added edges that go from either endpoint of one path to either endpoint of the other. Right, so I can set like x1 to be true, going from left to right or something. And then for x2, if I want to do x2 to be true, I'll go zigzag all the way across to get to the same starting point of the next path. Or if I want to set x2 to be false, I'll go down and go across or something, right? So these cross connections let you choose, okay, once I set x1 to be true or false, I get to choose x2 to be true or false, x3 is to be true or false. And you're just going to gradually make your way down, making choices whether you want to zigzag or go down and across. Okay, so we're going to set this, by the way, this is of course very clever in hindsight. So, if your question is like, how could I have thought of this? I don't know. Okay, so, so you're looking at solutions that might like go like this and then go like this, right? So these edges present choices for you that let you encode, true false statements or something. Okay, something like this. So that's the high level structure, and that's how we're going to model the variables, the decisions of our our formula. Okay. All right, so good. How many of those dots we have in the middle? We'll wait and see. Okay, so that's the high level initial design. But the thing we haven't really addressed is clauses. Okay, so you have some kind of framework where left or right we can interpret as setting the variable to be true or false. One rung for each variable. But we haven't said anything about the clauses, right? And you want to make sure that somehow you create something in the terms of graph language so that satisfying all the clauses should kind of correspond to a path through all the vertices. Yeah, I'm not saying this is like easy, but it's fun to think about. And of course, I'll tell you the answer in a moment. You will never get to think about it again. Or at least, yeah.
Operation, it's like if you want to be zero, so you have to go all the way like to the right, then you just have to connect the endpoint of that to the start point of x2, so that the only way you could go is forward.
For an AND operation.
For end operation, I don't know how you would.
Yeah, but in fact, we're already assuming we're in conjunctive normal form, which you have a bunch of clauses, which there's an AND of ORs. So, so you'll never have two variables ANDed together in a three-step formula, right? Because it'll be like three variables with an OR.
Acts as its own variable, right? It's a path.
Yeah. Well, okay. Well, sorry.
I guess I'm trying to figure out how to actually encode like the versions themselves. And so like an and between any two paths would mean connecting the endpoint of one path to the start point of another. So
Yes.
taking it one way means that you have to take the other one. That's it.
Yes. But keep in mind, I'm going to give you a formula that's already in conjunctive normal form, which means it's an and of like the or clauses. So you'll never get like x1 and x2. You'll get like a bunch of stuff and a bunch of stuff and a bunch of, and where each of those bunches is an or. You have to choose at least one of them. So I do agree that if that would model an and correctly. It's just that that's not our major issue. Yeah.
I think you could like put a vertex off to the side, and you can only reach it from like one of the arrows going down to the next path. So then, like if you ended up on the left side after you went through x2, then you can spend your time over this vertex before you go back to your main area.
Okay, yeah. So even taking a step back. Okay, so some level, the directions in code whether you're setting true or false, right? And like something like this, not x1 or x2, somehow it feels like if I'm taking a not x1 direction, okay, so we're going to create a vertex for the clauses as well, right? Because that's also like a requirement. Yeah, I mean, in terms of decisions and requirements, Hamiltonian path is kind of interesting because they're both sort of the form of the vertices. Whereas before with subset sum, we had a clear set of numbers and a target or something like this. Here it's a little more kind of homogeneous. But anyway, so for the clauses which represent requirements, we're also going to create vertices that you have to visit. And you can only visit once. And maybe we should set it up so that like like this first clause where x1, you want x1 to be false or x2 to be true, if you're going in x1's false direction, it should be very easy to visit this vertex. And it should be hard to visit if you're going in the wrong direction. And when x2 is equal to true, if you're going in x2 equals true direction, it should be easy to visit. But if you're going the wrong way, it should be very hard or impossible, right? Yeah.
Why can't you have an edge from like x2 to x1?
Why can't you have an edge from x2 to x1? Well, it's a free country, so you can always have an edge. But like in this, at some level, we're just trying to, at some level, anything that works, right? But here, I think we wanted to make a somewhat disciplined, rigid structure where you really have to choose x1 before going to x2, before going to x3, and knowing that you have to kind of traverse top down might make it easier to justify certain arguments later. I think if we had also like light blue edges going up and all across and all these kinds of things, it's not necessarily a priori bad or anything, but when it comes to proving things later, you eventually might want to say something like, well, a Hamiltonian path has to look like this so I can make certain observations and make certain deductions. And if you add lots of edges going all over the place, then it might be a little bit harder for you to pin down that, oh, a Hamiltonian path has to do this and has to do that and stuff like this. So maybe in hindsight, we can see, why the limited amount of degrees of freedom we allowed for is sort of facilitates the argument. At some level, anything that works. Yeah, so I'm not sure if there's a great answer to your question at the moment, but maybe we'll see. Okay, but going back to this point, let's add some kind of vertex. It's like you're traveling and you have to visit all these sites, and there's some places that are easy to visit on the way if you're taking the right road or something. So something like this, right? For not x1 or x2, I'll take two of these kind of pairs of vertices I haven't used yet. And okay, so this is set up so that if you're going x1 is equal in that direction, it's easy to just visit along the way and keep going, right? And in the opposite direction, if you're going in the friendly direction, then you just go visit it along the way. And it's going to be very hard to cheat, right? If you're going in the opposite direction, so you're going this way, and you visit here or something, right? You're cheating. You're not supposed to be able to do this. Then the only way to get out is like here. And now, how are you ever going to be able to visit this? Right? Because if you visit this somewhere later in your Hamiltonian path, you'd have nowhere to go. Right? So it's all set up that you can't really cheat. So the only way we should be able to visit this auxiliary vertex representing our clause is if you're going in the right direction. So the Hamiltonian path is quite strict. You have to visit everyone exactly once. Okay, so that's the idea. We can string up a bunch of these. Here's like another clause. Something like this. Or maybe you have another clause here from the rest of the graph or something. So you imagine, just to be safe, I'll make sure there's say 2m of these intermediate vertices so that I can just assign different pairs to different clauses and there's no cross-contamination. Just like this. And then it'll be very clear. This is not really drawn to scale, of course, but whatever. Okay, that's the high-level idea. So altogether, you'll get something like this. Okay, so if you want to prove this thing works, then you want to kind of go slowly through the if and only if, which as usual I haven't written out, but partly because it would bore you to death. So one direction is, if I had a satisfying assignment, let me describe to you a Hamiltonian path in the graph, right? And a Hamiltonian path is going to be like, well, if the assignment says x1 to be true, I'm going to go in this direction and false in this direction and stuff like this. And, I'll drop by and visit these clauses along the way for each of the literals that satisfy it, right? And they'll say, well, I'm able to visit all the clauses because for every clause, there must be some literal which corresponds to a direction that made it true because it was a satisfying assignment, right? Some jumble of words where you explain why it visits all the vertices exactly once. And in the opposite direction, if you imagine I drew out this ladder more fully, if I had a Hamiltonian path, okay, so first you know it has to start in one corner and end in the opposite corner. That's the only possible way. And it has to have sort of this zigzagging nature. And to do it fully, you might want to spend a little time explaining why, if you try to visit a vertex going the wrong direction, you'll never be able to complete a Hamiltonian path. Because then once you establish that, there's only one way to do it, then yeah, it'll kind of follow. So it'll be a little bit, awkward to write in full. You'll need a sentence taking care of a couple of details here and there. But ultimately, you want to just slowly and gently say, okay, if I have a Hamiltonian path, it must have certain properties, and with these properties, I can reconstruct a satisfying assignment, something like this, yeah? But once you establish both directions, a Hamiltonian path gives you a satisfying assignment gives you a Hamiltonian path, then you really know that your black box for Hamiltonian path will solve your formula, right? Yes will really mean yes, and no will really mean no. And of course, it's always awkward to write that paragraph because it's just awkward. But the first thing is to at least get the two directions correct. Okay, so that's the kind of thing. Now, one important thing to point out is we need to make sure the graph we make isn't like exponentially large, right? Because if I took my formula with like n variables, n vertices, I made an exponentially large graph and fed that to my black box that runs in polynomial time, it'll really be running in exponential time with respect to the original formula, right? Because I blew up the graph size so much. So we need to at least account for the graph size. So if I started with m clauses and n variables, how many vertices will this graph have? Roughly. Yeah, something like mn. So if we conservatively made all these paths long enough where every pair corresponds to a different clause, whether or not the vertex is even participating in it, then you'll just have m vertices on each of these rungs, right? And then there's n of these rungs of the ladder. So altogether, you're going to get a graph with mn vertices, which means there can only be, mn, all of that squared edges in the worst case or something. So, but if you're really careful, there's only mn edges as well because each clause can only have n variables. Okay, so that's the whole thing, right? So you put that all together, and we showed that, if you can find a Hamiltonian path reliably, then you can solve SAT formulas reliably in polynomial time. All right, that was kind of a lot. Any questions? I think with a lot of these constructions, it might just take a little time to absorb as well. Okay. But we do see a very dramatic difference now between DAGs and directed graphs, right? So a DAG you can even do in linear time, that's as fast as you can imagine. And a directed graph you can't do at all. You can do shortest path, you can do distances with negative edges, but you can't do longest path. Like maybe it's interesting to reflect on. So when we talked about DAGs, we had this creative solution of like, what if I just added -1 to everyone and just look for the longest path in the graph, in the DAG, by just doing Bellman-Ford on the DAG, right? And that would have worked. Why wouldn't that trick work for directed graphs? Yeah.
The negative cycle.
Yeah, so when we do distances, the negative cycle is you're allowed to just output negative infinity, right? So we at some level never have to really worry about the complexity of, if you imagine trying to write a dynamic program for Hamiltonian path or something, you'll start have to worrying about all the vertices you've already visited and stuff like this, right? And if you start enumerating all of the vertices you've ever visited, you'll start having like 2 to the n subproblems because every possible kind of history is another subproblem, right? And you can visit some subset of the n vertices. But if you're doing shortest, Bellman-Ford kind of distances with negative edges, when you find a negative cycle, you just say, oh, negative infinity and things like this. So you kind of have like an out, so to speak. So you don't have to remember all this kind of fine-grained data. Yeah. Okay. Good. Good. Okay, good. All right, so, all right, that brings us finally to undirected graphs. Okay, so undirected graphs are going to be somewhere in between. Well, not just because one is the extreme points, but in the sense that undirected graphs are a special case of directed graphs. I guess they're not really more general than DAGs. It's a little confusing. But in any case, it's a special case of directed, so there is still some chance for an algorithm. And also now your heuristic doesn't work because we've done one of each. So now nobody knows what will happen in chapter 3. So maybe I'll force you all to vote again. So last time it was 20% undirected, 80% directed. And let's see if the vote changes at all. Does anyone think we can get an algorithm for polynomial time? An algorithm for undirected? Oh, it went down. Okay, 3. And then does that mean the rest of you think it'll be hard? Yeah, okay, don't even, okay, so. Okay, so now most of you are even more willing to believe it's going to turn out to be hard. In that case, does anyone want to propose a way to show that the undirected version is also hard? Maybe maybe your question is, if I want to show undirected is hard, what's a nice choice of problem to start from? Yeah. Yeah, directed. I mean, we've often started from 3-SAT, but now we have directed graphs. That seems awfully close. So let's try to start from the directed setting, and now we want to somehow take a directed graph and turn it into an undirected graph, and somehow feed that into our black box for undirected Hamiltonian path. Okay, so somehow you want to take your directed graph and turn it into an undirected graph that still somehow is encoding the direction somehow, right? Like you can't do what I've drawn up there and just erase the edges. I mean, erase the directions because a Hamiltonian path up there may be using the wrong direction from the original graph. Okay. So, right, so now, but this is more guessable because at least we're going from graph to graph, and also graphs are easy to visualize and stuff and just more fun than Boolean formulas. It seems universally true. So, all right, so maybe I'll leave it, give you all a chance to guess or think. How can I take a directed graph and convert it to an undirected graph that sort of preserves the complexity of this Hamiltonian path problem? Yeah.
You split the vertex in the directed graph into an in and an out, and they're only connected, like x in and x out are only connected to each other, and everything that was going in the directed graph is just connected undirected to the in node, and everything that was going out in the directed graph is connected to the out.
Okay, so, well, now we're going to have a little time left. Okay, so take a vertex like this, like with some in vertices and some out vertices, right? And I think the suggestion was to do something sort of like this. Let me first imagine the arrows are still there. Right, something like this, right? If I had just first split the vertices, you've done this before when we like looked at vertex weights and stuff, so this is one of our favorite tricks, then, we haven't changed really the connectivity of the algorithm at all, right? You go in a vertex, now you just go across this bridge and you go out, right? And that's what we imagine, okay? And so I imagine, I can just erase these edges, right? And then in your mind, you're like, okay, you're gonna go in there, and you're going to go out. Right? I think that's what we all have in mind. And, I imagine a Hamiltonian path doing that in the undirected graph, and the direction doesn't really matter. Even if I was going from right to left, I could kind of reverse the whole thing, so to speak, and it's an undirected graph. But maybe there's one thing I should point out. What prevents something like this? So the Hamiltonian path comes into here and then goes out that way, right? And the Hamiltonian path later goes into here and goes out that way, right? So we're awfully close, but it's not clear to me that you couldn't do something like this, right? Because this is not the behavior we want, because this is now going in the wrong direction with respect to some of the original edges. Yeah.
You could add another node in the center so that you have to take
Okay. We'll add one more vertex in the center. And we'll do that for all the vertices. Okay? And now you can't really do this thing where you're coming in from both sides, right? You know, you can try to do this, but then, oh, no, I should have left that there. You know, maybe you do that side first, but then, you know, you can never visit this vertex, right? Because you can't get back out. So if we just add one vertex there in the center, then it's going to make a big difference. Yeah.
So in this construction, what stops you from going in the opposite direction of the original edge?
Okay. Yeah. So so now what prevents a Hamiltonian path from always going like this? In some sense, the way I drew it. Yeah.
That's fine. Now we're going the wrong way the whole time, so we can just imagine the whole thing.
Yeah, that's actually a better wording than I had. So if you're going like this, now I can still remember the names of the vertices, even though the graph isn't aware of it, right? So you're always kind of forced to go, if it was a normal direction, out in center, something like this, right? And if it was going the opposite direction, it'll always be having to visit in, out, center, or something like this. So it'll still be like, what we're pointing out in particular is that if it's going the wrong way, it has to go perfectly the wrong way. It has to go the wrong way through every vertex along the way. It can't suddenly correct itself, right? So if it's always going the wrong way, then we can just flip the whole thing over and then go the right way the whole time. So what really matters is that it's consistent and otherwise an undirected graph, so we can have gone either way. So that works out, but that is kind of worth in a full proof pointing out these kinds of things. Yeah.
Even if it does go the wrong way, so then it would follow kind of the reverse of the graphs that we're trying to find.
Exactly. That's what I meant to say, but I was clumsy with my words.
So does that still, like if there's a Hamiltonian path in the reverse graph, does that imply there's a Hamiltonian path in the original graph?
Well, so I think you want to justify something like, so first, any Hamiltonian path has to sort of have this out in center, or vice versa structure. You know, it could go in, out, center. That sounds awfully similar. I'm confused saying it out loud. So now you say, okay, now any Hamiltonian path is kind of one of these two orientations. It's going into orientation we imagine, in, out, center, out, in, center. Or it's going consistently in the wrong orientation, out, in, center, in, out, center, or something, right? So now you have it down to two cases. And then you say, well, if you give me a Hamiltonian path in the wrong orientation, it's going in, out, center, I could reverse it and get a Hamiltonian path that's going in the right direction.
But it would be going from z to x to y instead of y to x to z.
Yes, but it'll still be a path that visits all the vertices that you can lift to a Hamiltonian path in the original graph. It's exciting. Okay, so the black box just tells you yes or no. So it just says there is a Hamiltonian path. And then you say, okay, so let's say there's a Hamiltonian path. It's either going in the right direction or the wrong direction. At that point, you don't know. But then you can point out that if it was going the wrong direction, I can just reverse everything, and then I would get a Hamiltonian path going in the right direction. Hamiltonian path just means you visit all the vertices, and that's all that you have to worry about. Now that you have one that's in the right direction, then you can turn it into a path in your original graph. Yeah. You know, there will also be minor things to take care of, like it might be awkward if the Hamiltonian path like starts at a center or something. Somehow you have to take care of the endpoints and things like this, but yeah. Okay, so that's the trick. The vertex splitting trick was an extra vertex in the middle. Okay, well, I was prepared for this. Oh, well, here's another visual of splitting it, except it's actually not drawn correctly. There should be vertices in the middle. Okay. All right, so let's see if I remember how to do this. Okay, so here's maybe another problem. A Hamiltonian cycle is like a Hamiltonian path, except it's a cycle. So now you want to do a full loop through the graph. So that's awfully similar to Hamiltonian path. And indeed, it is going to be, basically equivalent. But this problem is still an exercise of whether you can prove the equivalence. So can we go from Hamiltonian path to Hamiltonian cycle? And can we go from Hamiltonian cycle to Hamiltonian path? Yeah, so this is more a challenge in playing with graphs. So let's see, which direction's up there first? Oh. Okay, so you want to decide if there's a polynomial time algorithm. So yeah, so maybe what we'll do is we'll start with a Hamiltonian path problem. So I give you a directed graph. The question is there a Hamiltonian path? And you have a black box that can answer whether or not there's a Hamiltonian cycle. Okay, how can I use a black box that looks for Hamiltonian cycles to find a Hamiltonian path? And any ideas? Yeah.
We could try adding one edge from every vertex to every other vertex and then plugging it into our black box every time.
Okay, so, all right, this is going fast. All right, so I have my original graph G, and I want to know, is there a Hamiltonian path? Something like this, right? So you want to know if there's some way to visit the whole graph, looking at every vertex exactly once. And the suggestion was like, okay, let me add a vertex here, and then I'll make sure that everyone can reach it, and it can reach anyone. Right? Is that?
That's a lot faster.
Oh, what did you have in mind?
I was adding a separate edge for every possible edge that could exist, and then I was plugging it into the black box every time.
Oh, okay. So, okay. Yeah, there's two options. Well, let me draw this one first, since I've drawn so much. So it's very easy to go here and here, right? So in particular for like this Hamiltonian path, once you get to the destination, you'd go to your super vertex you added, and you would go to your start, and that would be a Hamiltonian cycle. Okay? So if there's a Hamiltonian path in the graph, there will always be a Hamiltonian cycle in this extra graph you made. Maybe the other direction is, well, I don't know if it's just as easy, but we haven't shown the other direction yet. So in my graph where I added this super vertex, everyone can reach it, it can reach everyone. Suppose I find a Hamiltonian cycle in this graph. Can I argue that there's a Hamiltonian path in the original graph? Okay, everyone's nodding, so how or why? If I had a Hamiltonian cycle, how do I recover a Hamiltonian path? Yeah.
So we know to use that extra node at most once. So we just consider the cycle, but that must be a path.
Yeah, okay, so that cycle, whatever it's doing, it must visit our super vertex once, right? And wherever that point is, I can kind of split the path. At that point, like this, or split the cycle at that point. If you take a cycle and you remove, a connection, what will be left is a path, and it'll visit all the vertices. Okay, so that one's not too bad. So Hamiltonian cycle is equivalent to Hamiltonian path. All right. Well, okay. This is not maybe. Okay, this is more of an exercise. As far as equivalence of problems, we've already established that. But now, suppose you had a black box that solved Hamiltonian path, and you want to solve Hamiltonian cycle. So I give you a graph, and I want to know if there's a cycle that visits everyone. And all you can do is tell me if there's a path that visits everyone. So there's another, can you play some game with a graph? Again, I kind of forget the answer, but it seems like you're all very clever. So does the question make sense? So we're going to flip it. Now you have a black box that can find Hamiltonian paths. Can you use that to find a Hamiltonian cycle? Really hoping one of you solve it. Or maybe I'll give one more minute. Just everyone's got their game face on, so I'll just wait a little bit. Okay. All right. Who's got an idea? Oh, okay. All right.
So if the graph itself is a Hamiltonian cycle, then all the nodes must be like one single SEC. And so you can probably just take one edge out and then feed it into the Hamiltonian path algorithm. And if it finds, and if it finds it, then it must have been a cycle in the original.
Okay. So I'm going to remove an edge from the graph.
If it's all in one SEC, if it's not all in one SEC, then there's no Hamiltonian cycle. So there's no point.
Yeah, that's fine. So we can assume it's strongly kind of connected. Otherwise, it's impossible. That takes no time. And then now you're saying, okay, let me like delete one edge from the graph, right? And then feed it into the black box. And if it says there's a Hamiltonian path, then there must have been a Hamiltonian cycle in the original graph.
Yeah, there's probably some nuance about which edge you should be removing.
But you can try all of them, maybe.
Figure out. You can try all of them, yes.
Okay. But now let's say you try that edge and it says, oh, there's a Hamiltonian path. And maybe our black box is really strong and even tells you a Hamiltonian path. But the Hamiltonian path looks like this. So the Hamiltonian path is not necessarily, you're imagining that the edge will be like the last missing edge, but here's some like random cross edge in the middle. So the black box will say, yes, there's a Hamiltonian path. That doesn't mean there's a Hamiltonian cycle once you put the edge back in. Yeah? So that's one tricky part. Any other ideas? Yeah.
So like maybe you go the other way, like you take the Hamiltonian path and then you add an edge that would make it a Hamiltonian cycle, and then you just check if the graph has that.
Well, let's be careful when we say we go the other way, because the problem is very specific in the sense that if you can solve Hamiltonian path, can you solve Hamiltonian cycle? So if you're saying something like I'm going to add an edge and see if there's a Hamiltonian cycle, that's sort of the previous question, right? So the question you just have like a magical oracle that can tell you if there's a Hamiltonian path or not. Yeah.
It can't like verify it's a Hamiltonian path in like polynomial time anyways. So.
Yes, but the question is whether the existence of a Hamiltonian path implies the existence of a Hamiltonian cycle. Maybe there is a Hamiltonian path, but there was no Hamiltonian cycle or something. I mean, depending on what auxiliary graph you feed into it. Right? So, yeah.
So you basically this, but you have to copy all the incoming edges so that if you find whatever Hamiltonian path you find the other one, basically has to reach that same node twice. and if it's able to reach it a second time, then there must have been a cycle. But it represents a path in the graph.
Okay, so let's pick any vertex in our graph. Now, some of what we're going to do, imagine there's a Hamiltonian cycle. I'm going to just like break it and split it there. And then you can pick any vertex to split it at. So I'll pick some vertex in the middle of the graph. I mean, I don't know what middle means, but I imagine making some auxiliary graph where I make two copies of this vertex I removed, and then this copy will only have the outgoing edges. Maybe I should be more consistent, so there's 3. And then this one will have the incoming edges. Okay, so this is some vertex V, and now I have V out and V in, right? And if in this auxiliary graph there is a Hamiltonian path, right, it's kind of crawling all around and stuff. If there's a Hamiltonian path, then that should correspond in some Hamiltonian path where you, how do I draw this? So to be consistent, it'll look something like this or something, and then something like this. Okay, so if you find some Hamiltonian path in this graph where you split up that vertex, then you should be able to kind of glue it back together in the original graph. And in the original graph, if you have a Hamiltonian cycle, then that thing where you split up should give you a Hamiltonian path down here. Right? So you're either cutting the Hamiltonian cycle at this vertex to give you a path in this auxiliary graph, or you're taking a Hamiltonian path in this auxiliary graph and you're reconnecting it to get a Hamiltonian cycle in the original graph. And so that'll give you both directions of the if and only if. Yeah. Okay. All these little games. Okay. Here's the one we don't have to solve because we're kind of close to running out of time, unless you can figure out right away. But I'll just read it out loud because you get a lot of problems of this form. Okay. Like this was once a midterm question, I think. All right. So let's say I give you a graph. And like, how like when you play Super Mario, which is like before you were all born easily. But anyway, so there used to be something called like a Super Nintendo. Anyway, and so Mario goes around and he gets like a coin and you try to get a bunch of coins or something. But once you get a coin, you can't get it again, right? It doesn't like reappear. So same kind of deal. Imagine you have a vertex and there's like coins on all the vertices. And you started a vertex and you want to walk around the graph collecting as many coins as possible. Okay, but once you visit a vertex, you can't recollect it. So you can revisit a vertex, but you only get the coins once. Okay, so the question is, what's the walk in the graph? What's the maximum number of coins you can take walking through this graph? You can pick anywhere you want to start. You can pick anywhere you want to end, but you want to get as many coins as possible. Okay, and I can ask this question in a DAG, and I can ask this question in a general graph, and ask, okay, is this problem in polynomial time? Or is this problem as hard as, you probably have Hamiltonian path in mind, but, as hard as SAT? Okay? Yeah.
Can we do the same random longest walk length algorithm, but replace the one with the number of points?
Okay, so in a DAG, yes, we can basically do like a recursive thing where, maximum number of coins I can get from this vertex is my coins plus, I choose one of my neighbors. So that same algorithm, okay, will just basically be longest path in a DAG, except now you have vertex weights instead of edge weights or something. But what about a graph, a regular graph? I mean, just an arbitrary graph. Yeah. You're allowed to visit the same place multiple times, but you only get coins for visiting it once.
So can we just like SCCs and then do the same thing with the total coins throughout SCC?
Okay, very good. So this is the kind of problem I really like. So in this problem, right, it might feel a little Hamiltonian pathy because you only get points for visiting the vertex the first time. But you know how to solve it in DAGs, right? And if you have a strongly connected component in the graph, right, all these things can reach each other. You're going to visit all of them to get all the coins. So I can first take the strongly connected components of the graph, and when I combine collapse of vertices, I'll just add up the coin totals, right? Visiting one vertex is the same because then you'll visit everything. And now what's left is a problem on a DAG, which you just solved in part 1. Okay? So I think that's a great example of a problem, part B in particular, which would have been a little trickier if I didn't give you part 1. But part B is a problem where there was sort of implicitly a DAG because actually, reachability was kind of all equivalent. And once you take the strongly connected components, out comes a DAG. Okay, so you also get a handful of questions that are sort of in this space of like, okay, is this something I can solve, or is this really Hamiltonian path? Can I collapse things? Can I not? Can I pull out a DAG? Can I not? And I think that's a very good kind of exercise so that you can appreciate this tension between some problems that are solvable and some problems that aren't. Okay, thank you.